Hello AI enthusiasts, welcome to a new deep dive. Building on our previous talk about regularization and how it prevents overfitting, most tutorials show you how to train a model but skip how we know they truly generalize. In this video, we want to show something different, the hidden risk of the lucky split, and how cross-validation ensures your model is actually ready for the real world. When we train a model, we are essentially teaching it to find patterns in a specific set of data. But the real test is how it handles information it has never encountered before. Think of it like a chef preparing a signature dish for a food festival. We need to be sure the recipe works for everyone, not just one person. The simplest way to evaluate a model is to split our data into two parts, one for training and one for testing. However, this is like a chef practicing a new recipe for just one specific friend. If that friend happens to love extra salt, the chef might think the recipe is perfect, even if the rest of the world finds it inedible. In data science, we call this a lucky or unlucky split. If our small test set isn't perfectly representative, our accuracy scores become a roll of the dice. To fix this, we use cross-validation, which involves rotating our perspective. Instead of one split, we divide the data into several equal chunks. We train the model on most of the chunks and test it on the one we left out, then repeat the process. This rotation ensures that no single outlier in the data can trick us into thinking our model is better or worse than it actually is. Returning to our chef, this is like inviting 5 different groups of people on 5 different nights. On Monday, the chef tests the recipe with teenagers. On Tuesday, with professional food critics. By the end of the week, the chef doesn't just have one opinion, they have 5 distinct sets of feedback. By averaging these scores, the chef gets a much more robust and honest picture of how the dish will perform. Cross-validation is our best tool for spotting a model that is simply memorizing the data. If a model performs perfectly on training but fails on validation, it has overfitted. It's like a student who memorizes practice answers but doesn't understand the underlying math. Cross-validation exposes this gap by forcing the model to prove its knowledge on different subsets. Before we even begin the rotation, there is one critical step: shuffling. Imagine if our dataset was sorted by date. Without shuffling, our test chunk might be biased. By mixing the data thoroughly, we ensure each chunk is a representative sample of the whole. This creates a rigorous environment that leaves no room for the model to hide its weaknesses. In summary, cross-validation is the gold standard for model evaluation. By dividing, rotating, and averaging our results, we move past the uncertainty of a single test split. Just as a chef uses multiple tasting panels to perfect a recipe, we build models ready for the real world. Now you have the tools to ensure your models truly generalize. Subscribe for more deep dives into cross-validation.